All right, good morning, ladies and gentlemen. We're going to be going over the conservation of energy today. The law of conservation of energy, it states that the total energy of an isolated system remains constant. It's said to be conserved over time. So what does this mean? Total energy. If we say something like this, let's say we start with 10 joules of energy. We know how much energy we have to begin with. Then no matter what goes on in the middle, like whatever is going on with whatever we're observing, by the end of whatever we're looking at, we should know where all that 10 joules that we started with, we should be able to account for it all. Okay, so it doesn't disappear, it doesn't go anywhere. We can always keep track of where the energy is. An isolated system simply means that whatever objects we're looking at in the beginning that we include in our system of objects that we're observing, we just keep that the same the whole time. So there's not like random things being added, to whatever we're looking at. This law means that energy can neither be created nor destroyed. Rather, it is only transformed or transferred from one form to another. Okay, so for example, like going from kinetic to gravitational, that would be, transferred from one type of energy to another. So one of our best tools we have to just kind of keep track of what we're using are these energy bar charts. And an energy bar chart looks like so, right? We have our most common forms of energy up here at the top, and we're going to keep track of the motion of this pendulum right here. So very first thing that's important is we have, let me get my black color right there, right? We need to know where y equals 0 is. So y equals 0 is when we're dealing with anything with gravitational potential energy, we want to know where the lowest 0 point is. So now we have this kind of reference point. So now we're good. And I can start kind of looking at what type of energy is involved at each one of these points. Okay. Well, let's start at point 1. Point 1, it's at its highest point. So I know that it is at velocity of 0. There's no energy right there. Or there's no velocity. So that tells me there's no kinetic energy. It's not moving. So over here, I can put a little line at 0. Now, this is at its highest point. Right? It has its greatest height above 0 that this problem has. So let's say that all of this energy, and this is what always throws people off, let's just give it 5 blocks. We know it has all of its energy stored up in gravitational potential energy right here at 1. So we're going to give this 5 blocks of energy. 1, 2, 3, 4, 5. Okay? And there's nothing to do with anything stretching or compressing right here. So there's no elastic energy. There's no spring energy. So that's also 0. So all of its energy is involved in gravitational potential energy. Now at 2, take a look at what's going on. It is moving. So I know there's some kinetic, but it's still above 0, right? So maybe let's say this has 2 blocks of kinetic. So 1, 2. Remember, energy was conserved, so however much energy I started with, and I remember that doesn't mean 5 joules. This is just a representation, and it's a qualitative tool. So some of my blocks got transferred into kinetic, which means that I would have 3 left for gravitational potential energy because it's still above 0 right here. Still got some height, it's just not as high as before, so it has less gravitational. And still no stretching or compressing, so no potential spring energy. Now at 3, it is at its lowest point. It has a height of 0, so there is no gravitational potential energy. Remember, at the bottom of this swing, it's going to be moving the fastest. You can tell by looking at it. It's got the most little vroom lines right there, right? So all of that 5 blocks of energy is been transferred into kinetic. 2, 3, 4, 5, and there's still nothing being compressed or stretched. And then at 4, now we're all the way, to me it looks like we're at the exact same height as position 1. It has a velocity of 0 right there, most likely. Okay, so it's not moving. So we're back to 0. It has the greatest height right there. So all those 5 blocks are at gravitational potential energy. Nothing is being stretched or compressed, so I have no potential energy, spring energy. Okay, so you can see this just lets us keep track of where all the energies are and how much, like kind of how they're being compared. Okay, so this is like for a general, if we're looking at a phenomenon, we're wanting to keep track of everything throughout the course of this problem. With energy, what's nice is we actually only need to know the initial and the final states of an object. Everything between actually does not affect anything, right? We need to be able to keep track of all the energy that it starts with and all the energy that it ends with. And we can solve for a lot of stuff using this, and a lot of stuff quicker, which is nice. And so this is called a LOL chart, or an LOL diagram. You can see this is the LOL right there. Okay, so that's where it gets its name from. And we need to know the initial kind of phase of a problem and then the final phase of whatever we're observing. So the initial, we're going to keep track of all the energies that this problem starts with initially. That's going to be in the leftward bar chart. Okay, this circle right here in the middle, this circle is made to keep track of all the objects in our system. So right now, the system only has Biff, the water balloon that is getting thrown, and Earth. So you can notice Buffy, right, the initial Buffy, and this is just for an example, but Buffy is not in our system right now. She is outside of the system. So she is some, if she does anything to our problem, she's going to be some outside influence that's adding energy to the system. All right, the bar chart over on this side now is there to keep track of all the energies that we end with. Okay, so let's kind of walk through this and see how we can set this up. Buffy initially, let's see, if this is our height of 0 right here, right, she is above 0. So we're going to say that Buffy, and remember we usually just kind of use all the bars, so that's 1, 2, 3, 4, 5 blocks we have to work with. She initially she's up high, right? So gravitational potential energy. We're going to say the balloon, it's motionless to start with. Let's say this is the balloon right there. All right. So that balloon has an initial velocity of 0. And let's see what goes on. So the ball is not moving to begin with. Okay, so 0. She is way up high. So she has all of her energy, all of the energy in this system is included in gravitational potential energy, right? The reason why that's okay is the balloon is part of the system, and it's the balloon that's up high. So we can include that energy. The energy from these 3 objects is being included in our graphs. Now, in order for this thing to go up higher, notice we only have this much energy here so that it can get this high, right? The balloon. The balloon ends up going higher, which means it needs more energy added to the system. And the way that happens is Buffy throws the balloon, so she gives her own energy. She does what we call work onto the object or into the system. And so we draw an arrow from Buffy going into the system. She's doing work on the system, right? She's exerting a force and adding her own energy into the system. So let's say she's gonna add 2 blocks of energy. So we're gonna put little tick marks. 1, 2. And that's just to keep track of how much she's adding. Okay. So here I had 5. 1, 2, 3, 4, 5 blocks of energy. Now she's added 2. So when I draw my final bar graphs, I should have about 7 blocks of total energy. Okay, so when the balloon is now here, okay, well, if we take a look at that, that balloon is still at a height that is above 0, right? So that balloon is still going to have some gravitational potential energy. It's just going to be less than what it was before. So let's say it's now 2. Okay. So we still have 5 total blocks to account for. Well, this ball is moving right when it's about to land on Biff's head. V equals some final velocity. I don't know. So let's just say it's greater than 0. Right? It's moving right before it hits Biff in the head. So we could say that all that energy went to kinetic. Okay. Thermal energy is a new one. We don't have a special symbol for that one. It's not a potential. It's not an anything. So we just call it thermal energy. This is basically the energy that's kind of like our dumpster. We know when things change shape, when things just get hit, whenever, like if the temperature raises from friction, anything like that, if friction or anything takes any type of energy, it gets put into thermal energy. And so we know that we have accounted for 5, 1, 2, 3, 4, 5 of those 7 blocks. So because this balloon gets misshapen and probably heats up a little bit, and there's some friction of the balloon on the head, we're going to say that that goes into the thermal energy account. Okay? So this is our qualitative way of keeping track of everything. Now, if we wanted to talk about what is actually going on here, the nice thing this does is it lets us write out our energy equations. So we have remember, if energy is conserved, if we add together, so if we net all the initial energies, that should be equal to the net of all the final energies. Right? So let's take a look at what we have here. We would have initial, the only energy we have here is initial gravitational potential energy. So that's gravitational potential energy, initial. Now, Buffy is doing work on the system, right? So she is adding her energy. So we're going to say plus work equals the sum of all these energies right here, which would be kinetic plus the final gravitational potential energy plus this is thermal energy. We can just put ETH for thermal. Okay, and this would be our final, just kind of qualitative energy equation right here. This keeps track of all the energies we have to begin with. And if we needed to, the nice thing is we know the expressions for all of these types of energy, right? We could say initial gravitational potential energy is mg y initial, the initial height, plus, remember our equation for work, FD cosine of theta. Kinetic energy is 1/2 mass, and this is in the final energy state, so that would be its final velocity squared, plus the gravitational potential energy that it finishes with, so mg times the final height. And then whatever, remember thermal is basically like the big dumpster bin of energy. That's like where heat and friction and everything puts its energy, so we don't have an expression for that. We just put it as E thermal. Okay? So when we need to start solving for stuff, this is how we're going to keep track of all the energies involved, and we can now just rearrange any of those equations and solve for a specific variable that it's asking. All right? So I will catch you all on the flip side.